Good morning, class. Any volunteer to pray? Any volunteer, especially a Muslim today? A Muslim can lead us with a word of prayer today. Sean? Any other volunteer? Bryson? There's no volunteer. Will Jaden? Jaden? Okay, Wilson or Rina? Wilson or Rina?
Okay. Let's go ahead for another prayer. Lord Father, grant us understanding in this session. Help us understand what we're going to study. Amen.
Thank you very much, Orina. Let us directly begin from the basics as we advance. From our previous lesson, we learned something about number 8. We are beginning from number 8 on your screens. Compass needle is placed below a current. Can you underline that word below? Below a current, carrying conductor is shown below. You can see the diagram. Indicate on the diagram the direction of the current. Indicate on the diagram the direction of current. First, we needed to know the rule we must apply in this equation. Which rule are we applying in this question number 8? Alan? Shikanga?
The Ampere swimming rule.
Ampere swimming rule. Then, how will these swimmers, which method will we use for the swimmer to determine the direction of current? How will the swimmer swim to determine the direction of the current, in this case number 8?
I think it's a backstroke.
Backstroke, eh?
Yes.
So, akitumia backstroke akielekea juu ama chini?
Akielekea juu.
backstroke akielekea juu, so that the left hand iko side ya North Pole.
Yes.
Therefore, the direction of current will be towards the south or north.
Towards the north.
Yes, thank you very much. It means you know the Ampere swimming rule. That was it shows that you are very attentive in our previous lesson. Anna, you have something to say? Sean, we proceed to the next question. Question number 6. You also mentioned something about question number 6. And even from the diagram, we can know the rule we are going to use. Which rule will be appropriate for number 6? Which rule will be appropriate for number 6? First, before you tell us the rule, that symbol X, what is the meaning of that symbol X? 26,243. 26,243. Can you briefly discuss that question? Remember, this is a topic of discussion, and discussion is based in this topic. Discussion and demonstration is based in this topic. Proceed.
Excuse me, Chair.
Yes.
I was asking a question.
Yes.
Number 8, is it a backstroke or is it in number 8? Because I believe the backstroke should be when the compass is above the conductor.
Yes.
In number 8, the person who
Yes.
answered said the person is swimming in a backstroke, but the backstroke is swum when the compass is above the conductor.
The question is, a compass needle is placed below. The compass needle is placed below the conductor, below a current carrying conductor is shown. We underline below. So there is something we should know about below, and when the current carrying conductor is below, and when it is above. You are still on phone.
Yes.
Who is this? 243.
Yes.
Yes, give us your point of explanation.
Okay, I was saying that if the compass is under the wire, the swimmer should not be swimming a backstroke. Instead, it should be opposite. But when the wire is below the compass needle, then the swimmer should go in a backstroke. That's why the direction of current should be towards the south, not the north.
How will the swimmer swim in this case? How will the swimmer swim? Towards the north or towards the south?
It's the direction of current should be towards the south.
And the position of the swimmer, how will the swimmer swim? Where will the left hand of the swimmer? Yes?
It should be opposite from the backstroke.
The swimmer, we are all in agreement that the swimmer will swim using backstroke method. Is the swimmer swimming above the current or below the current?
Above the current.
Above the current. So anafaa kulalia for this case, the North Pole will be, you have to imagine you are a swimmer now in this one. So the swimmer will be using backstroke, but in the opposite direction.
Yes.
Meaning the direction of current will be facing the from north to south.
Yes.
We can look for other. We have several questions. We can handle several questions of such. But before we go to any other question of this sort, let us first finish number 6. Let us first finish number 6. So we are using the meaning of symbol A and B in question 6. You first must know the interpretation of this symbol. First must know the interpretation of this symbol. Is it current up or current down? This one is current. The X is current down. And we are using the right hand rule, right hand grip rule. And the thumb will be pointing the thumb for question 6A will be pointing towards the south. The thumb in question 6 will be pointing towards the south. And also in B, it will be pointing towards the south. Can you now indicate, we need to indicate the direction of current of magnetic field. We need to indicate the direction of magnetic field in both A and B. And they should be concentric in nature. They should be circular in nature. A and B should be circular in nature. Enos? Enos? So in B, in question 6, let me share the screens. We have this symbol and this other symbol. And we have already said that this is current up, this current down. So both of them will form concentric we are showing it on the screen. We are showing it on the screen. The first one was current. We have current down, both cases. So we indicate someone is misbehaving with the screen. Someone is misbehaving with the screen. We are in question 6. So in part A, the direction of magnetic field will be in the anti-clockwise direction in both cases. The direction of magnetic field will be in the anti-clockwise direction in both cases. And you must indicate the current, the direction of the field with an arrow. But we must consider each part individually, part A individually and part B individually. So part A, the current will be moving. The current will be, the magnetic field will be moving in anti-clockwise direction. And in B, the current will also be moving in anti-clockwise direction. Question 7 requires the same concept. Question 7 requires the same concept. We have current up in A and current down in B. So we use the rule. How do you use the rule? You have a pen in your hand. So when current is moving up, we are using the pen as our conductor. So when you hold that pen facing in the upward direction, the magnetic fields, the direction of magnetic fields will move in the, is it clockwise or anti-clockwise direction in part 7A? Part 7A, current will move in the anti-clockwise direction. And in B, current is moving downwards, meaning if in the first case, case A, you are holding the pen upwards, then you will change the direction of, you will change the position of holding that pen. The pen, you will hold the pen downwards. The pen for this case is the conductor, meaning the current will move in the clockwise direction in B. This is what we are talking about. I'm sharing it now. Can you consider this question? Sketch the resultant magnetic field. Sketch the resultant magnetic field patterns when the current flow in both wires in the direction as shown. For this case, a question can come in this, and a question can be asked in this manner, where the arrows are showing the direction of current. So you use the right-hand grip rule, and the thumb will be facing upwards, the direction of current. The magnetic field will therefore, in part A, the magnetic field will be moving in an anti-clockwise direction. We also determine part B individually. The current is also moving upwards. We use the right-hand grip rule. Your pen is a tool of demonstration in this case. And the current is moving upwards. So the direction of magnetic field is also in the anti-clockwise direction. There is something you need to know about this. Let me share. There is something we need to know about this current conductor. Something about force, the force acting on it. So that there is a magnetic shield. There is a magnetic shield that we need to indicate in those two diagrams. But before indicate those magnetic shields, I want you to note the following here. There is a force on a current carrying conductor in the motor effect. From this concept, we'll be able to understand how the magnetic shield is happening as a result of force. Now, let us consider this setup in this diagram for a conductor carrying current in a magnetic field. We have we'll go back to that current up and current down after this concept. We have the magnet with the north pole and south pole, and we have a conductor carrying current. The direction of force has been indicated, but in every diagram here, we must apply the rule, and this is where some of you also had challenges in determining the direction. All these rules, they relate in different questions in this topic. So this diagram has indicated the north pole and the south pole. It has also indicated direction of current and the direction of force. How we get this is by the Fleming's left-hand rule, as indicated below here. And I noticed that some of you forgot to know the first finger and what the first finger signifies and what the second finger represents. For the thumb, we had no problems. The thumb points the direction of force. The first finger points the direction of magnetic field, and the second finger direction of current. It is important to note this, and for understanding purposes and demonstration, let us kindly, with a pen, can you indicate that the thumb is force F? The first finger is magnetic field FMF, and the second finger is current I. And as we do this question, we know that fields normally originate from the North Pole to the South Pole. Fields always originate from the North Pole to the South Pole, meaning the first finger, which is pointing the direction of magnetic field, will point toward the right. The second finger, which represents the direction of current, will point towards the will point in the direction of current in the conductor. Hope you can see the conductor on the screen. We are considering this first diagram. So the first finger is pointing towards the South Pole. The second finger is pointing in the direction of the conductor, and the force is the thumb. The direction of force is the thumb. I want someone to show us in a video, in your camera, how you will twist the arm such that the North Pole, the first finger is pointing towards the south. The second finger is pointing in the direction of current of this conductor, and the thumb is pointing in the southwest direction. Someone to show a video. Someone to show how you will hold your hand such that from this diagram, the magnetic field is pointing towards the south using the motor rule or the Fleming's left-hand rule. You must test. Someone to show us that. How you will fix your hand, which are mutually held at right angles, such that the three fingers points in these directions. 26, 243. Is it possible that you share your camera? The question is, we are considering this diagram in the screen. we are considering this diagram in the screen. I want us to use the Fleming's left-hand rule such that in this first diagram, the first finger which shows the direction of magnetic field is pointing towards the to the right side. The second finger, which shows the direction of current, is pointing in the direction of current, and the thumb is pointing in the direction of force. 26 to 43.
Can you make me start my video?
Yes?
I can't start my video because the host has disabled it.
Mm. Allow. Let me try to allow. Let me allow. Hope you have noted the question somewhere, just as in the diagram. So that is 26, 243. Twenty-six, 243. Ngila. Ngila, you have disappeared. Maybe the best way to do, we can we can discuss a question then. Let me share a question here. Let us consider this question, though we did it last time. Let us revisit question 17. And we are using the same rule. So in question 17, the North Pole, we have the North and South Pole as in the diagram. We also have the conductor carrying current XY, and we have the source of current. We have the source of current, and the current is flowing through XY. The current is flowing through XY. How do we know that the current is flowing through XY? How do you know that the current is flowing through XY? A point? Ambrose? Ambrose? Yes.
The positive from the positive terminal.
Yes.
Current from the positive terminal, the current flows.
We see from the terminals. So the current is flowing towards X through Y. So meaning, if the current is flowing from X to Y, the finger indicating current should be pointing towards Y. So can you fix your left hand finger? Can you first ensure that you are from Fleming's left hand rule, your fingers are mutually at right angles. Then the finger indicating the direction of current should point towards Y. Begin from that. We are using the diagram. The finger pointing towards pointing current, that is the second finger, is pointing towards Y. Tukianza na hiyo, the finger pointing the direction of current pointing towards Y, the direction, the first finger will be pointing toward the right. So we must twist our hand such that the finger showing the direction of magnetic field, which is the first finger, is pointing from north to south without changing the direction of the finger pointing the direction of current. So the first finger will be pointing downwards. The second finger will be pointing towards Y. And the thumb will automatically point, is it to the right direction or to the left direction? Bradley Ocheng? Bradley Ocheng?
To the right. To the right.
Yes, to the right. Let us consider starting from hiyo tumeanzia finger ikiwa current ikikuja towards Y. Tunaweza anzia finger showing the direction of magnetic field. Can you let the finger showing the direction of magnetic field point from the north to south? Meaning the first finger will point downwards. I hope we are moving together. Let the first finger, which is showing the direction of magnetic field, point downwards. The direction of current is flowing from X to Y. So make sure the second finger is pointing towards Y. And the thumb will automatically, if you're holding your three, if you're holding them mutually at right angles, the thumb will automatically point to the right. We can now answer the question. State and explain the observation made on the conductor when the switch is closed. When the switch is closed, meaning current is connected, so the current will flow. And the effect on the conductor XY, the conductor XY will move towards the supports. It will move towards the support. That is the first mark. The conductor will move towards the supports. So when current flows along XY, the conductor rolls along the fields towards the support. In which direction does XY experience the force? In which direction does the wire XY experience the force? The force is moving to the right. The force is moving to the right. How do you determine the direction in one above? How do you determine the direction in one above? This one requires us to use a rule. This one requires us to use the rule. We are using the
Fleming's left hand.
Yes, Fleming's left-hand rule. And when is the force on the XY greatest? When is the force on XY greatest? When? That is a one more question. When is the force on the XY greatest? The force in the XY is greatest when the angle between the conductor and the magnetic field and the field is 90 degrees. It is greatest when it is 90 degrees. If you don't want to say when it is 90 degrees, you can say when. If you don't want to say when the angle between the conductor and the field is 90 degrees, you can also say Shikanga.
When the conductor and the field are perpendicular to each other.
Yes, when the conductor and the field are perpendicular to each other. What is the effect of reversing? What is the effect of reversing both magnetic field and the direction of flow of current? We are changing the position, the directions. We are reversing. We are reversing the direction of magnetic field and the direction of current. Meaning we are interchanging. The north will be downwards and the south will be upwards. Now the direction of flow of current, which will not be towards Y, it will not be from X to Y again, but from Y to X, meaning for us to change the direction of flow of current, we are also changing the terminals such that the current is flowing from Y to X. This one we must sketch. We must sketch this. Kindly don't interfere with the whiteboard. Don't interfere with the whiteboard. We are now changing the direction of magnetic field such that the North Pole this is a South Pole and North Pole. Then the direction of current is y to x. So we use the left hand, Fleming's left hand rule. We use the Fleming left hand rule to show the direction of. Can you sketch and respond to how the effect of reversing both the magnetic field and the direction of current, flow of current? Someone is saying it still rolls outwards. Will the direction of force be in the same direction with the first case? Will the direction of motion of force be in the same direction with the first case? Yes. You can say it still rolls to the right, or there is no effect. It remains the same. There is no effect on direction of force. The direction of force will not change. The direction of force will not change. The direction of force remains to the right. I wanted someone to still show in a video, but the video is who can try to demonstrate using the video by sharing your camera. Rambui. Rambui. Name the instrument which uses this effect. Name the instrument which uses this effect. Enos.
An electric motor.
The electric motor. Yes. Let us consider this question.
Focus too.
Back to this question. Ten. Show the direction of magnetic field. Show the direction of magnetic field in the conductor carrying the current shown below. Show the direction of. If you know the rule, you know the answer. If you don't know the rule, you don't know the answer. We have the iPhone 13 Pro. Give the answer in terms of clockwise or anti-clockwise. Yes? Proceed. $269.
Anti-clockwise.
Anti-clockwise, eh? Reason? Reason? Why anti-clockwise direction? Enos?
Teacher,
Yes.
is it really anti-clockwise or clockwise? It's current carrying down. So if you
Current
use
down.
the right hand, it'll be clockwise.
Yes. The magnetic field is moving in the clockwise direction. Now, as we said before, it seems some of you still don't know the representation of this X and the dot. X shows current down and the dot shows current up. So if you are using your pen as a conductor, you will grasp your pen such that the thumb is facing downwards and that the tip of the pen is facing downwards, meaning that is the direction of current. And the four fingers show the direction of magnetic field, the way they are curved. So the direction of magnetic field will be in the clockwise direction. What will happen if we bring the same? Let us now consider number 12, question number 12. We have current moving upwards and we have the magnet, meaning we expect magnetic fields. We expect magnetic fields in that diagram. We expect magnetic effect. First of all, we must know that fields normally originate from the north to the south. So the arrows should be pointing towards the south pole. The arrows will be pointing towards the south pole. Any trial? Explain what you are going to do in this question number 12. Enos.
So because it's current going upwards, the
Yes.
second finger will be the one which will be facing upwards. The first finger should face towards the left direction because it's moving from the North Pole to the South Pole. Then automatically the thumb will point something downward. Yeah.
So the direction of force is upwards.
Yes.
The question requires us to show the direction of force. So the direction of force will be pointing upwards, and you use a ruler. Use a ruler to make that from you use a ruler from this point of current up. Then you show an arrow pointing upwards, and on the and then you indicate F to show that is force. You must also indicate F to show that it is force. Name the polarities. Number 13. The figure shows a current carrying conductor in a magnetic field direction of force on the wire is shown by the arrow. State the polarities of A and B. We are in number 13. Can you state the polarities in A and B?
Okay.
In A, let us give Sami a chance. Sami?
A is north and B is south.
Reason? Why is A North Pole and B North Pole and B South Pole?
The direction of force, and if you use the left hand grip rule, the Fleming's left hand rule, the direction of force, the magnetic field is moving towards B.
The direction of? Apart from that, how can you determine that A is North Pole and B is South Pole? There is something you should mention about magnetic strengths. Mention something about magnetic strengths.
Yeah, I'm not sure about that answer.
Tobias?
Cha, when you're asking about magnetic strengths, are you saying we find out how the magnetic lines are moving?
Moving, yes. Let us begin by finding how the magnetic lines, field lines are flowing, moving.
Oh, so
then the path with stronger magnets will cause this effect of force being pushed upwards. Can you note that question somewhere as I share something here? Note that question number 13 somewhere. Remember that we have been asked about the polarities in A and B, and there is a current up, and the force is moving in the upward direction. Then we consider this. Point number 3 here, the magnetic field concentrates at the top of the conductor than at the bottom, thereby creating a region of strong field. The reason for this is that the field due to electric current is the conductor. The reason for this is that the field due to the electric current in the conductor and that of magnets reinforce each other since they are directed in the same direction. What is the meaning of this statement? When magnetic fields are moving or are heading towards the same direction, meaning when they are moving towards the same direction, when the fields are moving towards the same direction, if we consider that representation of current moving downwards, where the magnetic fields and this one of where the fields move in the same direction, it means it is concentrated in that region than the other region. Let us take an example of this one. Part B, we have current moving, current up, and we have current down. And when we indicate the magnetic fields, we can see the direction of magnetic fields. In the first case, when the current is moving up, the magnetic fields are moving in the anticlockwise direction, and this other one, the magnetic fields are moving in the clockwise direction, meaning the fields here will repel each other. And since the magnetic fields are heading in the same direction, it will cause a region of more concentration, and that region of more concentration will create a stronger field, which will push the other region with a weaker field towards the right in the second case and towards the left in the first case. So there is the effect of concentration of magnetic field when moving in the same direction, and when the concentrations are more in one region, that is a region with stronger field than the other one. So the fields in this case, the fields between the conductors repel each other since they are directed in the same direction, and a force therefore acts on the conductors to pull them apart outwards. Back to that other question. From the question we were solving previously, It means the magnetic fields were concentrated in the lower region, and it resulted to the force being pushed upwards. For this case A, parallel conductors carrying current in the same direction. Parallel conductors carrying current in the same direction. The magnetic field between the conductors is weaker due to cancellation and than the field from the outer side. So back to this question. States the polarities in A and B. So someone had already mentioned that you can use the rule where we have the direction of force. We use the motor rule or the right hand and the left hand, the Fleming's left hand rule. That was Victor. Eh? That was Victor. Omari? Omari? Enos?
Teacher.
Yes. Still in question 13.
No, now question 12.
Yes.
You said that the direction of motion or direction of the force on the conductor will be upwards, but I thought it will be downwards because considering the poles and the magnetic field, direction of magnetic field, if you apply the Fleming's left-hand rule, direction of motion will be downwards, per se.
Let us apply Fleming's left-hand rule. Let us begin by sketching this. Let us begin by sketching that somewhere. Can you sketch that somewhere? The current is moving up. So the first finger, the second finger, which shows current, direction of current is pointing upwards. Can you twist your finger such that the direction of magnetic field, which is the first finger, is pointing, and we are using the Fleming's left-hand rule. pointing in the direction of towards the left, towards the south. Current is pointing upwards. Current is pointing upwards. Where will the thumb be?
The thumb will be facing downwards.
The first finger is facing to the left.
Yes. The second finger is facing upwards because current is moving out upwards.
Yes, current is moving out.
Yes. Then the thumb will rest downwards in the southern direction.
The thumb can use the diagram directly to we can use the diagram directly to use we can use the diagram directly to apply the rule. I want us to move together. The first hand, which is show the direction of magnetic field, is pointing to the
left.
To the left. Yes. Then the current is moving outwards, meaning we twist the direction of the second finger to face upwards.
Mm-hmm.
And they should be mutually held at right angles.
Yes.
Yes, you are right. Meaning the force will face downwards.
Yes.
To question 13, can we also apply the same rule?
Yes.
The current is moving. Let us begin from the point showing current. This is current upwards, current out. So the second finger is pointing upwards.
To the right. No, to the right. The second finger is to the right. To the upwards.
Yes, we are considering number 13. We are in question number 13.
Oh.
Yes, we are in question number 13 now. So the second finger, which shows the direction of current, is pointing upwards. The force is pointing
upward
in that direction.
Yes.
Meaning the first finger will be pointing towards, is it towards A or towards B?
Towards B.
Towards B.
Yes.
So we repeat for the sake of the rest. Number 13. We begin with current out. So the second finger, which shows the current, is pointing upwards. The force is pointing in the horizontal direction as indicated, meaning the first finger will be pointing towards B. Mm-hmm. And we know the poles, the fields normally originate from the North Pole to the South Pole. So the first finger is pointing towards B. meaning B is the south pole and A is the north pole. Yes, I hope we are moving together. Enos?
Yes.
Yes. We go to question, we apply the same rule in question 14. The figure below shows a conductor, Y, placed in a magnetic field. The conductor carries a current flowing into the paper. Hata hii number 14 imepeana int. Current is flowing into the paper. Remember in the previous questions, haikuwa inatupea int ya kwamba this is current upwards or current out. Current out or current down. So we know the representation of X that this is current down. We have already been given the ukipewa magnetic, ukipewa north pole na south pole, that means imekopea direction of magnetic field. The magnetic field will be, the first finger will be pointing towards. Now, can we now move together in number 14? Can we move together in number 14?
Yes.
We have 9 minutes left. In number 14, the first finger, we are using the diagram. Can you make sure that the first finger is pointing? The first finger indicates the direction of magnetic field. So the first finger is pointing towards the south.
To the right. Yes.
To the right, yes. The first finger is pointing to the right.
Yes.
This is current down, meaning
Yes.
the finger pointing, the finger showing us the direction of current will point downwards. So we
Yes.
twist the, after using the first finger to point the right direction, we now twist the second finger, which shows the direction of current downwards. And that one will automatically give us the direction of force. What is the direction of force in this?
Down.
Let us give someone else a chance. 377. The force will be moving in which direction? They should be mutually held at right angles. That is 377, 26, 377.
Downward.
Yes, downwards. Sketch the resultant magnetic field. Sketch the resultant magnetic field between the poles. Sketch the resultant magnetic field between the poles. If the force if the force is pointing downwards, it means this region, the downward region will be a region of will it be a region of stronger magnet or weaker magnet? Remember the part with the which is more concentrated pushes the other part. So the direction of force indicates that it is concentrated in the upper region. The direction of force is downwards, meaning the upper region of this representation of X is concentrated. And the lower region is bulging outwards. Let me share the answer for this part? We have 5 minutes left. Draw magnetic field line such that the upper region of this representation X is more concentrated than this other the opposite region, which is toward the south, since the force is pointing downwards. That is what we are talking about in question 14. So the diagram should appear as in question number 14. Show on the diagram, we have already shown the direction of force acting on it. The last question in the next 2 minutes, before we are ending our class in the next 2 minutes. As earlier mentioned, in the application part, that is an example of application question in this topic. Any of the applications can be asked. The motor, we have already gone through the question on the motor. Name the parts. You must be able to know all the parts of those. This is an example of a simple electric bell circuit. So in these application questions, you can be told to label, can be asked to label the parts. You can be asked to explain the working of this simple electric bell, or the working of the motor, or the working of the circuit breakers, and so on. Let me just ask this one question here. What is the use of the capacitor in this? Capacitor. Makori?
to reduce the sparking effect at the contact.
Yes, very good. To reduce the sparking effect and the contact. Someone is asking, please tell where I can find this question. Think I can send it through the form administrator. All the questions in this topic, I'll send it to Mr. Onyango. I think we'll send them to the groups. All questions in this topic right away after this class. Thank you very much for your cooperation and active participation during this lesson. Have a nice time.